Hello, this is Britt Caswell with another example video. In today's video, I'm covering example 1 from lesson 8-1 in the SavvasRealize Algebra 1 textbook. The goal of today's video is to identify a quadratic parent function. There's a lot to unpack in this example, y'all. This is a lot of vocabulary. So kind of put on your boots and let's go. So when we talk about the quadratic parent function, we're talking about this equation right here. Okay, it says that f of x is equal to x squared. Notice there's nothing being added or subtracted to it. There's nothing being multiplied to it. Alright, so this is a parent function. Alright, what makes it a quadratic parent function is that it is x squared. It's the simplest function in the quadratic function family because there aren't any transformations happening to it. Alright? Now, when we graph this function, our graph produces a certain shape called a parabola. Okay, it's a U shape that you see here. Alright, so parabolas, they can either face upwards like you see on this example, or they could face downwards. But you will never see parabolas go to the left like this or to the right like this. These are called hyperbolas, and we cover them in Algebra 2. Okay, so parabolas will always go up or down. All right. Now the first thing that I want to talk about with a parabola is right here, the itty bitty point where the two sides of it kind of curve down to. All right. So this point here is called the vertex. On our parent function, that vertex is 0, 0, but that vertex could be anywhere on the graph depending on what we add or subtract from the equation. All right. Now that vertex can be a minimum or a maximum of the graph. In this case, it's a minimum. But notice, see, it's the very bottom of the graph. Or if our parabola was one of the ones that faces downwards, it would be the top part of the graph. Okay, so that fact that it is a minimum or a maximum is what makes the vertex so useful. All right, now quadratics, they have a lot of varied uses. Okay, they reach across almost every subject matter I could think of. Some of their biggest applications, when you throw an object or when an object is in free fall, which you might have heard of in physics, all right, it's going to follow a path called parabolic motion. So it follows the path through the air the same way that a parabola does. In fact, when I teach this live, I have a ball and I throw it at people so that they can see the parabolic motion. Okay. This is used in architecture a lot. All right, this is used in manufacturing because it has to do with area. So this is a really, really big concept for us. And like I said, it's used in many, many different contexts. So let's keep going about parts of it. So that's why the vertex is important. Now, what I'm going to do is I'm going to draw a vertical line that comes through this vertex. Now, when we graph parabolas, we don't usually draw the axis of symmetry, which is what this is called. However, it's very important to know that it's there. All right? So the axis of symmetry, or for something to be symmetrical about an axis, means that if I were to take this graph paper and I were to fold it in half along this line, one side of my parabola would map onto the other side. And you could see that symmetric part right here, right? You could see that it's mirrored. All right, now the axis of symmetry is a line. So what that means is when you go to describe the axis of symmetry, you need to do it with the equation of a line. All right, so it's always going to be x equals and then some number. All right. Now in this case, that number is 0. And you get that 0 from looking over here at your vertex's x value, because the vertex always lies on the axis of symmetry. The other thing that we look at is which direction the parabola opens towards. So in this one, our parabola opens upwards. But if we had reflected this graph over the x-axis, so if it was flipped this way, this parabola would open downwards. So there's two options, upwards or downwards, that a parabola can open. Oh Lord, I am not writing that well. There we go. In this case, the graph is opening upwards. So now the try it, and this part that I wrote in, this is an extension that I came up with. It's not part of Savvas, but it's good for you guys to understand it because you're going to run into this soon in math. These are taking you towards more complex ideas that we're going to investigate further in this chapter, okay? So the try it says, when are the values of the function positive and when are they negative? Now remember, if it says f of x, that means y. So this is asking for what x values, okay, that's what it means by when. So for what x values are the values of y positive and when are they negative? So for something to be positive, right, we would look here on the y-axis. And if you notice, almost all of our graph is having those positive y values, with the exception of a single point. Do you see how our vertex is on the ordered pair 0, 0? That 0, 0 is not positive because 0 isn't positive. So what I would say is, I'm actually going to type this out so that you guys don't see my messy handwriting. Oops. I don't want that, I want this. Okay. So I'm going to say the graph is positive for all x values except where x equals 0. The graph does not have any negative y values. Alright, so this parabola does not go down into the negative section for the y's, and it's positive for every value of x except for that vertex where x is equal to 0. Alright, so this part we're going to look at increasing versus decreasing. So what I want you guys to imagine for this, I'm actually going to use blue, is I want you to imagine a guy on a skateboard. It's actually kind of a long board, huh? And he has a GoPro on his head. So when we are determining increasing versus decreasing, this dude is going to go on his skateboard, he's just going to roll from the left-hand side of the graph to the right-hand side of the graph. And so he's going to be keeping his eyes on the graph as he continues. And the direction that his eyes travel, either upwards or downwards, will be whether it's increasing or decreasing. Alright? So as he's coming from the left, do you see on this side of the graph, on this leg, how he would be going down with his GoPro? He'd be looking like going down. So what that means is that this part of the graph that I'm highlighting in red is decreasing. Okay, so if I wanted to describe that, I would say it's decreasing when x is less than 0, because it's that negative side of the graph there. So then our dude man, he's going to keep riding his little GoPro, or his skateboard, and he's coming this way still. He passes the vertex, and now, look, do you see how his head would start going upwards? So this part of the graph that I'm highlighting in green is increasing. And so the way that I would describe that is when x is greater than 0. Now notice it's changing directions at the vertex, right? It goes from decreasing to increasing. So when you have a vertex, the graph is neither increasing nor decreasing. Okay, so I'm going to actually put that in our little notes here. At the vertex, the graph is neither increasing nor decreasing. And so here's why that's important is when you go to write these inequalities, do you see how they don't have the equal to bar? That would include 0, but 0 is not included in either of those. Okay. Now our last thing that I just want to touch on real fast is the idea of the zeros of a function. The zeros means the x-intercepts, okay, where it crosses the x-axis. Another word is the solution. So on this one, our parabola comes down and touches the axis at the vertex and then turns away. So this one has 1, 0 at x equals 0. Now if I do a translation and I slide the parabola down, I could have 2 zeros. Okay? If I slide the parabola upwards, I could have no zeros. So the number of zeros tends to be kind of a big deal for people. We'll get into that a lot more in, I want to say it's like 8.3. Okay? But just remember that it's the solution or the x-intercept. So there we have it, guys. That is how to identify a parent function and a whole heck of a lot of vocabulary about it. Until next time.